In this video, we're going to take a look at vectors, vector-valued functions, motion problems using vectors. So let's first off start with the definition. A vector V is a two-dimensional construct from an initial point P. So if you've got some location P to Q, the P is known as the tail and the Q is known as the head. And it can be written as PQ with a little arrow above to match the direction of the vector. Vectors have length, also known as magnitude, which has the symbol double bar of V. If a vector originates at the origin, it is called a position vector. Otherwise, if you are given the coordinates of the start and end, then every vector has an x component and a y component that can be thought of a and b, where a is the difference of the x values and b is the difference of the y values. And then the length or magnitude will be equal to the distance formula, which is the square root of a squared plus b squared. And a vector of length 0 is actually called the zero vector. And vectors are written just with these coordinates, or this like AB notation. And unless otherwise stated, they're just assumed to start at the origin. Now, vector algebra is fairly straightforward. If we have a couple of vectors, so say vector V and vector W, then if we want to add these vectors together, we can simply think about starting with vector V and getting to this coordinate and then adding on vector W to that, which ends us up over here. Or we can go with the W first and then the V second. You would end up in the exact same place. And the final vector that you end up getting is this vector here. So when you combine these together, you end up with this vector V plus W, which is basically the diagonal of this parallelogram that gets built. And this works if you have 3 or 4 or 5 vectors together. You can add them in any order, and you just get a resulting vector, say V plus W. And it works with subtraction V minus W as well. For scalar or multiplication, we have a symbol, lambda, and the scalar factor of V is just taking your original V vector and applying a scale to it. So if you had a lambda value of 2, then you would just end up doubling that vector and going twice as far in the direction that the V is going. And so in general, if you have two vectors, say V plus W, and you know that, say, V has components A and B, and W has components C and D. If you want to do addition, you would just add the x values of both. If you want to do addition, you can add the y values of both. If you subtract the x values and subtract. And then if you apply this lambda, then you apply the lambda to the x direction, and you also apply the lambda to the y direction. As well, vectors can be linear combinations of other vectors. So for example, we could express U, the vector 4, 4, as a combination of V and W, V being 6, 2, and W being 2, 4. And the way that we go about doing that is we think about vector V is going to have some scalar, we'll call it S, applied to it. And so really it will instead look like 6S times 2S. And we'll apply another scalar, we'll call it R, to W. And so this will look like 2R and 4R. And when I add these two vectors together now, I will get 6s plus 2r's for the x value, and 2s and 4r's. And now all I want that is to be my u. And so I want this to be equal to 4, 4. And so I can solve this system. I can solve this to get s is 2 over 5 and r is 4 over 5. And so I can know that the vector 4, 4, the u vector, is equal to 2/5 of the v vector and 4/5 of the w vector, 2, 4. As well, another thing about the vectors is that a vector of length 1 has a special name. It's known as a unit vector. And that unit vector, let's see, it's E, will have, say, coordinates cosine theta, sine theta, so that it is got a length of 1. And to find a unit vector E that's in the same direction as another vector V, we can use this formula. So the E vector will be the V vector divided by the length of the V vector. That will force it to have a length of 1. For instance, if you have a V vector of 3, 5, then the unit vector for 3, 5 is the square root of 3 squared plus 5 squared, which is the square root of 34. And so this E vector will be your 3, 5 vector. So let's write it as a vector. So the 3 and the 5, but the 3 is going to get divided by root 34, and the 5 is going to get divided by root 34. So you apply a scalar to it and shrink your vector. A unit vector that is directly along the x-axis is notated or denoted by just the letter I. And of course it is unit length 1, so it will end at 1, 0. And if you want to have one that goes along the y-axis, we call that j. And of course it starts at the origin, it will be 0, 1. And these are known as standard basis vectors. And every single vector that you can make can be made up of I and j. So you can think about any vector being made up of some scalar a times the unit vector I and some scalar b times the unit vector of j. Once we have this idea, it's not too far to push it to taking a and b and making them into functions rather than into just a static vector. So the vector actually now can describe a path. And these are known as vector value functions. And we can actually even combine this with parametrics. So we have a function whose x value is changing with respect to time and whose y value is changing with respect to time. And we can really think about that as the scalar of the x coordinate and the scalar of the y coordinate. And we can start to use this to do some calculus. We can find limits for vector value functions. So what we're doing is really describing a path's, actually we're describing the vectors of that path. So the first vector started here, then there are vectors starting here. We're moving towards this vector called u at time t0 along the path r of t. The more technical way of showing this is given with this notation, which uses these new angled brackets to describe how the limit gets applied to the x function and the limit gets applied to the y function. So let's try an example of this. So given the limit as t goes towards 3 of the function r of t, and we'll give r of t as the vector t squared, comma 1 minus t, then I just apply the limit to each piece. So I apply the limit as t is going towards 3 for t squared, and I do the same as t goes towards 3 for 1 minus t, and this is equal to 9, negative 2. And so that's the limit approach to this, which means we can start to do other types of calculus. once we can apply limits, so we can find derivatives. And so essentially, if we want to know the derivative of r of t, we just have to take the derivative of the x component and then the derivative of the y component, and that will be our vector. And we can do second derivative, we can do third derivative for these. As well, we can apply the sum rule, the scalar rule, the product rule, even the chain rule can be applied to all of the vector value derivatives. And we can also integrate vector valued functions. And so we would get the integration of this being equal to, using FTC1. So for example, we can use the integration to do applications, so we can find the path of a particle, and we can find its location, say, of this particle whose speed or whose r dr dt is changing at a vector rate given. This should be the vector symbol, and we can find the location, as I said, of where it is at a certain time, like t equals 4. If we know the initial vector at time 0, so we can find r of t by taking the integral of that vector with respect to t. We can solve this to get the vector t plus 2 cosine of 3t and 1 over 10t squared. Of course, there's some constant that gets added on. I have r of 0 is 4, 1, so I can set up the first piece. So I can therefore know that the vector 0 plus 2 cosine 3 times 0, comma 0 plus some c is equal to this 4, 1, so at the initial condition. And I can solve this to get my c is the vector 2, 1. Then I know that my r of t is equal to the t plus 2 cosine 3t, but I add 2 more to that vector, and then it's 1 over 10t squared, added 1 more to that component of the vector, and I can go back and calculate what r4 is, and it's approximately 7.69 and 2.6. And so there's the resulting vector on this path. So here's an example of this. If you get a Mars rover and it starts off at this 0.65 and it's traveling along this curve in this direction and on 0, 2, and you have a function for the change of the x as time goes on. You have a function for the change of y as time goes on. We want to know where is this rover at time equals 1. We'll assume this is in meters and hours. So the y value and x value, so let's start with x. X time 1 will be equal to, well, it starts at 6 in the x direction, and then there's a change from 6, and that change can be measured in that 1 second time by just taking the derivative, antiderivative of x prime t dt's equation. And we can just do this on a calculator. So we can just plug in the function 12 sine 2t squared into this, and we can get a location for the x value, and y of 1 starts at 5. It goes for a while from 0 to 1 at its rate of y prime. And this one is, if I plug it into the calculator, at 4.057 in the y direction. I'll leave it to you to calculate the x coordinate using your calculator and filling this one in. You can find the location of this Mars rover after 1 hour. Okay, that's it.